Start. Okay, Volodya, you can start.
So 1 minute wait. It's not yet 9. Maybe someone. Okay. So I will use this 1 minute to thank all of you, to thank all organizers, and especially Andrei and Vanya for this invitation and for this possibility to speak so long. It is a rare option, and I'm very, very grateful. And also, I want to use this time to wish you, all of you, very good mood at the end of the year, and best wishes for New Year, best wishes for all seasonal feast, like correctly now people says. So Happy New Year and good health and best mathematics in the new year. So I start today my third lecture, and my third lecture, I remind that we are speaking about multiplication kernels. We spoke about Bessel operators or quantum operators, and we discussed briefly from the very beginning two families of polynomials, Buchstaber family and Kontsevich family. And today I will concentrate on these two objects more precisely. So I remind that all of them are connected, all these subjects are connected. They are connected in this double tetrahedron, Kontsevich, Buchstaber. Common property, very important, that they are discriminantly split. And also there are two vertices which also connects all these three families of polynomials. One vertex is a structure of two-valued group, especially important, and it is very amazing that the most important and simple, the elementary two-valued group, which defines by the simplest polynomial. I showed you this simplest polynomial, this multiplication given by two roots of this polynomial, and this polynomial is here. Z2 minus 2 times x plus y, z plus x minus y2. Next time, maybe in New Year, I will tell you how this polynomials appeared in very, very interesting subject of Landau discriminant singularities in various problems of amplitude scattering in computations of Feynman integrals. So it is just a very, very important object, and maybe it will be subject of my next talk, but not today. Okay, so we stopped yesterday, not yesterday, we stopped last time at the interesting combinatorial problems, and these interesting combinatorial problems are also related to my kernels and my polynomials. For example, for this polynomial, which I mentioned today a few minutes ago, this polynomial defines so-called singular locus of the kernel D module, and it has a very beautiful geometric property. It can be factorized in after proper change of coordinates. I want to say that these squares of coordinates in physics, which I mentioned, they play the role of mass, particle masses. So, and the corresponding function in particle physics called Clausen functions, and it was introduced by physicists independently, this delta 2. All this combinatorics also relates to interesting integrals, interesting kernels, and now how all these stuff relates to Buchstaber and Kontsevich polynomial. The first remark I made, we can generalize these polynomials for any n, considering multiplication formulas for any n, and we get a family of polynomials which independently Buchstaber and Vladimir discovered in middle 90s. And these polynomials, they are all very, very nicely looked. Look, it means that all of them are discriminants. This second polynomial that I told you, it is called Landau discriminant, but also all other polynomials, they are also discriminant. It is possible to write as a discriminant of some quadratic equation. And you can just play with this. For example, for n equal to 4, it is a very, very nice exercise. I told you about relation with mirror symmetry, and then we stop when we consider some integer sequences which one can obtain from coefficients of this kernel and Bessel kernel development. We don't know all meaning and all interesting properties of these integer coefficients, but the very fact that they are integer, and some of them are in this OEE's encyclopedia of integer sequences, shows that the very object is quite amusing and deserves to be studied and discussed. And today I will start to put the light reminder on some addition laws which are important in my story for Kontsevich, generalized Kontsevich and Buchstaber. So the simplest addition law is, this is addition law on elliptic curve. If you have an elliptic curve, then there is a following observation. Taken, for example, if you have this elliptic curve in Weierstrass form, like here, and this that gives you this one differential on the elliptic curve, dx over y. It's a square root, means that y square equals, I omit 4. Usually people put 4 here, but it doesn't matter. You understand that I have this one form, and integrating this form from 0 I make a choice of 0, and then I integrate it from 0 to P1, from 0 to P2, and then we obtain that there is a due to abelian addition law, the third point which we can define using this P1 and P2, and these two integrals modular modular lambda, I mean the lattice defining this elliptic curve, it is exactly an integral from 0 to this third point. We can conditionally write this addition law like P1 plus P2 equal to Q1. And that's what usually people call simplest form of abelian law on elliptic curve. But we also can generalize following Abel this addition law in the following form. Instead of this integral identity, we can consider a linear bundle, line bundle with connection, and taking differential equation, Pfaff differential equation, d psi equal to psi omega. And then the solution of this differential equation, psi in the point P, it is an exponential, which gives explicit, if you want, very, very clear explanation why this law is really addition law, which can be also related to multiplicative form of this law. So the sum of these two integrals expressed in this integral between 0 and q1, our addition law, it is the same like multiplication of this exponential form. So psi p1, psi p2 equal psi in the point q1. And in this form, of course, we can go further and can generalize this observation. Following to Abel, it's a classical thing. We can consider the rational differential. I think that Andrei knows this subject much better than me. But anyway, we can integrate this rational differential between origin 0 and set of big N points. And then Abel discovered the following theorem. We can reduce number of these points and express some of these integrals as a sum of integrals between 0 and p points, where p is substantially less than n. So y1, yp. Of course, it is modular sum corrected term, which is a holomorphic or rational function e. And in this, in this form, this theorem admits immediate generalization, what we called non-abelian generalization of Abel theorem. What is a non-abelian generalization? We just consider now, instead of line bundle, we consider vector bundle, and instead of the first order differential equation, we consider nth order differential equation. And in this non-abelian form, our theorem can be expressed very easily like a kind of multiplication kernel form. So remind that we have eigenvalue for lambda, for eigenfunction psi, где L some differential operator which enters in some ordinary differential equation. This eigenvalue we will call following tradition an accessory parameter. It means that a local monodromy doesn't depend on lambda. And then we want to find solution phi 0, holomorphic solution of this eigenproblem corresponding to this accessory parameter lambda or eigenvalue lambda in 2 points x and y. And then, as I told you from the very beginning, we want to present it as integral over some cycle from the kernel, which doesn't depend on lambda, and phi 0 in point z, where z is an integration variable. So we write this solution in terms of this generating functions. The coefficients of the generating functions will be polynomial in my accessory parameter. And then the recipe how to find such kernel was proposed in some beautiful, simple lemma of Kontsevich and Buchstaber. We will introduce the structure constant, which defined some algebra structure on the coefficients of my generating functions. So I suppose that they are polynomial, and I take a basis such that all members of my basis have the corresponding degree of the index. Constants, P1, it's degree 1, and etc. And then product of two coefficients of degree I and degree j, it gives you some, with this structure constant series. And this structure constant can be defined as a kernel in the following representation. Take the kernel as the sum of this structure constant x to I, x to j divided by z k plus 1. So this kernel, it's one differential form because we want to integrate it. And the integral, just Cauchy integral, because we have this pole. So we have this residue formula for products of two eigenfunctions. So we have our eigenfunction in terms of this series using the coefficients C, I, J, K for products of these coefficients and define this kernel, and then the multiplication formula for solution gives us explicit formula. And in this form, we can generalize it as a kind of, it was not in Odesky and Kontsevich, it was in some sense our philosophy. We can generalize it like a form of non-abelian-Abel theorem. So we can take, like we did it here, instead of sum of integrals, we can take the product, and we can take the products of psi in different points and take it like integral of kernels of so we can integrate it like a kernel which depends on all parameters, including y, yp, and then it will be a kind of Odesky-Kontsevich formula, but the kernel will depend on many variables, and that means that we can use, instead of polynomials in one accessory parameter, we can consider the polynomials of n or g accessory parameters. So we have in our formula we have reduction from g plus 1 to g, and then from g to g minus 1, etc. So we can always use the same story, the same kernels to reduce number of integrals like in the initial Abel theorem. Okay, I'm sorry for this imprecise because I didn't want to go in details. If you want, you can consider now preprint of 2021. And then I remind you that how this Kontsevich-Odesky lemma, for example, gives our Sonine Gegenbauer. We can go to our Bessel, n's solution of n's Bessel. We can write the kernel of corresponding of this solution in the form of Odesky and Kontsevich, and then we proved that our approach, which gives some period related to hypersurface, toric hypersurface family in this toric space of dimension n minus 1, relates exactly to this kernel which one can obtain from Odesky and Kontsevich formula. So our kernel and the period, they are exactly have the same formal series expression. So formal series for this integral, which we proved, and formal series which one can obtain from Odesky and Kontsevich, it is the same. It's just direct verification. Now, I want to make some digression, because to explain how Buchstaber polynomials and, for example, Buchstaber Ries polynomials appeared, it was clear, but how general Buchstaber polynomial and generalized Kontsevich polynomial related to the Buchstaber, how they appeared initially. Then I need to the following reminder. What is the formal group law? Let's consider some commutative ring R. In applications, of course, R will be or integer or real or complex numbers. And then, of course, it might be also polynomial rings with the coefficients in this number rings Z, R, and C. And we will consider the formal series in two variables, U and V. And then we say that the equation W equal to phi of UV define the classical formal group law over the ring R if two simple things happens. First, if we take second variable equal to 0, then this series trivializes to the first variable U. Now, second, if we take and instead of V put phi in V and some third variable W, so we have this substitution in the second place. Or we can make this substitution on the first place and put instead of U, phi of UV, and then take the variable W. Then the corresponding series are coincide. It means that we have some associativity constraint. This is associativity. Associativity constraint. So we have two very simple conditions. Now, what people knew about it? For example, they consider different constructions of formal groups. Why it is interesting, I briefly said, because they came from topologies, they came from study of cohomology spectra and generalized cohomology, like K groups, like cobordism, etc. And they were introduced in topology by Buchstaber and Novikov. But the theory of formal group, before it was a part of number theory and it was a part of algebraic geometry. It was used by French school in works of Lazare. And so it was in United States, it was Dwork, and in Japan, it was Honda, who studied formal groups. And of course, number theory people used it very, very widely. But in topology, very special type of formal groups, very interesting. Simple, but very important. And one of this type is so-called square moduli formal group construction. What is this square moduli formal group construction? It is the following. Let's suppose that we have some formal group, this formal group phi UV, which satisfy to these two axioms. And then we can consider a polynomial of three variables, x, y, z, quadratic polynomial, which is written in the form z squared minus θ1 xy z plus θ2 xy equal to 0. Of course, from general it's general knowledge that this series is, because we suppose now that coefficients of this function, they are series. So it is a function in series. So this θ1 and θ2, they can be imagined like sum and product of some series z plus and z minus, which are considered like a root series for this quadratic equation. And then we say that two-valued formal group, of course, it's two-valued group because it's a generally, like I showed you from the very beginning, we can define two-valued multiplication, but formal. And this two-valued formal group is called square modulus if there is another initial formal group phi such that z plus, it is a phi uv phi u bar v bar, which gives you square of module for f of u. We will suppose that now our field, basic field is C. And that's why the name square module, because this root is a square module of this formal group phi. And z minus also square root of module phi u bar v. So if we have such a formal group, then we have original formal group phi, then we have two z plus, z minus. They define some roots, and these roots gives you series is theta 1 and theta 2, and this series is theta 1, theta 2 define the two-valued group law for these roots. So why it is typically in topology? Because if we start now with simplest possible initial formal group law, just U plus V, which then this group law appeared, formal group law, which starts with U plus V. It's connected with the usual cohomology theory, and the corresponding construction of this square modular group gives us polynomial bxy, and it is very, very surprising, but very nicely appeared again our delta 2 square polynomial, or what I told you, polynomial which appeared in physics, in particle physics, for under the name of square of Calan function. So it was the first example of two-valued group which Novikov and Buchstaber in topology considered in 1971. And then if we consider initial formal group U plus V minus Q, U times V, where Q is a complex parameter, then they used such group in usual case theory, considering like extraordinary cohomology theory, and the corresponding polynomial, which in the construction of square module, it is a polynomial which contains a part of this quadratic part, cubic term q square minus q square xyz, and this is nothing but singular. If we consider this locus of zeros and consider this locus in corresponding projective space, then we have so-called nodal Cayley cubic surface, which is a very famous and very well-studied object in algebraic geometry. And then, of course, it was a kind of problem. What general properties of polynomials of this type, bxyz, which gives this law of square modular formal group. And Buchstaber in 1990 classified all two-valued algebraic groups which all groups which come from this square modular construction. He used Krichever results about Baker-Heiser elliptic function addition theorems, and then he proved that there is a polynomial B, from which I start my talk, which depend on three parameters, A1, A2, A3, and this polynomial generally it general degree is 6 because it is part of products of xyz degree 3 in square root 6, and this also maximal degree is 6. But if you consider this polynomial as a function of each xyz, it will be quadratic. It will be quadratic. And the form of this polynomial in Buchstaber results also is very specific. It is a square of this expression. You remember, I denoted by sigma 1. This I denote by sigma 3. So it's sigma 1 minus A2 sigma 3 in square minus 4, 1 plus A3 sigma 3. And this is sigma 2 plus A1 sigma 3. And then Buchstaber also proved that these parameters, they are not arbitrary, but they are parameterized by some elliptic curve, which in standard Weierstrass presentation is written like V2 equal to 4U3 minus these modular parameters G2 and G3, so G2U minus G3, and my parameters A1, A2, A3 now should be related to this curve in the following way. A1, it's a value of P function, Weierstrass P function in some point alpha, so we have some point on this curve. We consider Weierstrass function P alpha, multiplying by 3. The second parameter should be square of this value of P alpha times 3 minus G2 divided by 4. And A3 is P alpha cube times 4 minus G2 P alpha minus G3 divided by 4. So if we have such parameterization, then this polynomial governs some formal group of this square moduli type, like I explained. Of course, this looks miraculously, but in fact, it is not so miraculously, because if you have this elliptic curve, then you can apply to elliptic curve the following construction, which was also proposed by Buchstaber long time ago together with Ries, or maybe without Ries before. It is so-called two coset group construction. This is a very general construction for any coset G over H. One can define the formal two-valued group. And in this case, when you have this elliptic curve epsilon, you have a product epsilon times epsilon quotient by the involution. So this epsilon times epsilon, it is a typically, so you have abelian group structure addition law on Xi, and Xi times Xi also have some group structure, and a modular involution, it has some coset, and if you take this construction formally, you apply you obtain some two-valued group, and this is exactly what Buchstaber had. So it is not so, but it was not also, it was also looked miraculously how these parameters can be related to this elliptic curve point alpha. And only very recently, in fact, in 2019, Buchstaber and Sasha Veselov, they proved the following beautiful theorem. They said that if we have this polynomial with A1, A2, A3 defining multiplication form, then we have a locus polynomial equal to 0. And of course, we can make now the following observation. Of course, it need to read Whittaker and Watson and so on. First idea: what kind of addition law might be? What kind of this group structure on the product of elliptic curve quotient by involution you can obtain? And of course, with elliptic curve, there is many forms of addition law if you have different uniformization of your elliptic curve. The uniformization with P function is more natural because Buchstaber proved this theorem about link of his parameters A1, A2, A3 with P function. Then Buchstaber and Veselov observed that if we introduce this point alpha and P in the point alpha, and then take the following change of variables, we introduce variables x big, y big, and z big, such that all variables x, y, and z, which satisfy to the equation of Buchstaber polynomial, they are inverse to P function in x plus p function in alpha, p function in y plus p function in alpha, and p function of z, and p function of alpha. And then they wanted to look what the law one can define on the big X, big Y, and big Z if small x, small y, and small z are points on this locus in one hand side, and in second, they expressed with the help of p function. I remind you that p function has its own very interesting addition law. Addition law for p function. Of course, I can write it explicitly. P of u plus P of v with minus plus P of u plus v minus 1/4 square P prime of u minus P prime of v divided by P of u minus P of v. I think I wrote properly. So P in the point u plus v equal to sum of P of u plus P of v, and this term in square. But it is better, if you want, it is better to write this law in a very beautiful, more simple way, which is much easier to have in mind. You can write it in the form of so-called Frobenius determinant. This Frobenius determinant has the following property. You have 1, 1, 1, P of u, P of v, P prime of u, P prime of v, and P of u plus v, P prime of u plus v equal to 0 if u plus v plus double r. Okay, you see, I forgot myself. It's better to write like this. P of u, P of v, P of w, P prime of u, P prime of v, P prime of w, and here it's P of no. Okay, yes, 1, 1, 1, 1, 1. It is easy to check that this is equivalent to the equation which I wrote, but one can rewrite this equation in the form, in the algebraic form, if we consider the polynomial of Buchstaber type with coefficients a1 equal to 0, so we can make choice of point alpha such that P of alpha equal to 0 here. And then the second coefficient a2 and third a3, they will be minus g2 over 4 and minus g3 over 4. And then the Buchstaber polynomial will have this form. First term is square, but no xyz here because of this condition a1 equal to 0. And here you have coefficient 4 because a1 equal to 0. And this product of 1 minus g3 over 4 xyz. And this is exactly the solution of this condition for P. This is the addition law for polynomial This polynomial is addition law for P function. So what this polynomial gives you in these coordinates x, y, and z big. Buchstaber and Veselov proved that this addition law is equivalent to simplest possible addition laws like x plus minus y plus minus z equal to 0. So this linear addition law in inverse coordinates correspond to the addition law in terms of Weierstrass function. Of course, it looks miraculously, but now I want to get this miracle in the following way. I will introduce Kontsevich polynomial, second polynomial which I started with. You remember that Kontsevich polynomial also has special discriminant form, and it is also symmetric in XYZ like it was in Buchstaber polynomial, and he was constructed in the following way. Let's take any algebraic monic polynomial of degree 3 with coefficients a, b, and c. And then subtract from this cubic f, we will subtract t minus x, t minus y, t minus z. So we suppose that x, y, z, they are roots of this cubic. And then factorize it and subtract. When we subtract, the term t square, t cube minus t cube, this term will disappear. And we have a quadratic trinom. And this quadratic trinom has discriminant of this form. Explicitly, in each variable, this polynomial can be written as a quadratic polynomial. So we can take the second discriminant. For example, here, this is discriminant in t. It's discriminant in t, but we can take discriminant in z of this. And discriminant in z will gives you f in minus x, f in minus y. If we redevelop it, and because it's completely symmetric, we obtain that each discriminant in x can be factorized f minus z, f minus y. In y, it might factorize f minus x, f minus z. So it is so-called strongly determinant splitted polynomial. And this fact that this polynomial also relates to some elliptic curve addition law. Namely, let's consider this cubic like the cubic which gives equation of elliptic curve. On the plane, we have roots x, y, and z. Here they are. 3 points. X, y, and z. In these points, we can consider these roots like abscess of 3 points on my cubic P1, P2, P3. They correspond. So the relation law between addition and addition on elliptic curve, the relation between addition and my these roots, it is very, very straightforward. So it means that my polynomial Kontsevich introduced in the context of Landau's should relate to Buchstaber polynomial, which appeared in the framework of this two-valued formal group of square module type. So it was a small challenge to explicitly rewrite Kontsevich polynomial in terms of Buchstaber. And of course, this Buchstaber-Veselov change of variables was very helpful. Namely, with Ilya and Buchstaber, we proved the following theorem. if we have this generalized Kontsevich polynomial, it is as I told you, strongly factorized, strongly splitted in each variables if we take in its determinant, and then we can make the change of variables minus 1 over x, minus 1 over y, minus 1 over z, and change of parameters a1, a2, a3 by minus a, b, and minus c. Then up to this square factor, we have explicitly Buchstaber polynomial with parameters minus a, minus b, and minus c. It means, in particular, that this Buchstaber polynomial can be also considered first as a discriminant, type of some quadratic polynomial. So we have this in parameter t, this cubic, this development of in terms of roots. Now roots are minus 1 over x, minus 1 over y, minus 1 over z. And then if we rewrite this discriminant, then we explicitly obtain Buchstaber polynomial. It's a simple statement. But what is much more interesting that we proved the following classification result, that all symmetric polynomials with three variables, x, y, z, degree 2 in each variables, which admit this splitted discriminant property, this splitted discriminant property, they also should satisfy the formal group identity. It means that they should satisfy to these conditions for second order quadratic equation in each variable. If we take, for example, y equals z, then this polynomial should have form x minus z in square. If we take x equal to 0, this polynomial should be y minus z in square. And if z equal to 0, then this polynomial should be x minus y in square. Then each polynomial of this type exactly coincides with this form of Kontsevich-Buchstaber type polynomial. So this polynomial is a polynomial of Buchstaber proved long time ago in the theory of formal groups. That's more or less all my story today. This story a little bit shorter than all other, but I want to finish my talk also with the following. This theorem, it is not only the result about this change of variables, because we also started a common locus for these polynomials. And this common locus has interesting geometric property. It might be also written like a product of some Lotze equation, and each Lotze equation has interesting interpretation in terms of so-called Baville surfaces in algebraic geometry, but this is still should be better understood. But I want to say that this change of variables and this I would say parameterization, it has also very beautiful geometric how to say geometric images. For example, if we take the 0 for this Buchstaber polynomial, which correspond to my addition law, for this Buchstaber polynomial, which correspond to this addition law in terms of p function, that, as I told you, the corresponding formal group, it is the E cross E over involution. It can be considered like a kind of Kummer surfaces. So we have beautiful, we have, oops, no, sorry. We have beautiful Kelly cubic. This is a Kelly cubic. And we have this beautiful Kummer surface. It means that probably we can establish some links between interesting algebraic geometric surfaces and this family of polynomials which enters in the general Buchstaber-Kontsevich construction. For example, these Boville type surfaces, they are different. They give different link to theory of algebraic geometric surface. This question should be studied better. Now I stop here. Thank you for your attention.
Okay. Thank you. Thank you. Very nice talk from the three parts. Thank you for any parts. Okay, very interesting.
Thank you for your patience that you had time to hear it. In fact, this story is endless. If you want, one can go further and further. One can go to the story of Feynman integrals and scattering amplitudes and topological behavior of Landau or discriminant singularities. Everything is so. Everything is linked to this.
I ask you some questions.
Probably it's too many, too much for one.
Sorry, I have some questions.
Yes,
Questions concerning elliptic curve and
well, can you a little bit louder, Tole?
I just wonder about elliptic curve, your construction based on some group law on elliptic curve with 3-second rules, and it immediately generalizes for abelian surface varieties. And my question,
Not immediate, but of course there is this theory of sigma functions, Weierstrass P generalized so-called Weierstrass hyperelliptic functions, which were developed again by Buchstaber, Renolsky, and Dimoleykin. And in this theory, there are addition laws. And of course, they have also interesting applications in integrable systems. What I don't know at the moment, how it relates to the multiplication kernels of Kontsevich. This I don't know. But of course, we should think in this direction. For abelian, for hyperelliptic curves, at least. I don't know if I answered your question.
okay, thank you for answer. Okay.
Okay, let us thank our speaker again. Thank you, Volodya.
You and
very nice talk. Thank you very much. Okay, we can stop. We can stop our seminar.